Good morning, everyone. My name is Khushi from BSc Chemistry Honors second year, and my topic is Carboxylic Acid chapter. Introduction. Carboxylic acids are acidic compounds having one or more carboxyl groups, which is C double bond O, OH, or COOH in their molecules. The name of carboxyl is derived from the combination of the term carbonyl and hydroxyl. The carboxylic acid are classified as mono, di, or tri-carboxylic acid according to the number of carboxyl group present in the molecule. Nomenclature. Common system. The aliphatic monocarboxylic acid are commonly called fatty acid as many of them, particularly the higher members, occur in natural fats. The common name of individual fatty acids are derived from some of their natural sources. For example, formic acid is so derived as it was obtained from ants' formica, since acetic acid derives from actum vinegar. Other branch chain and substituted acids are named as appropriate derivatives of straight chain acids. The position of side chain and subsequent groups can be indicated by alpha, beta, or gamma. Aromatic acids have the carbonyl group directly attached to the aromatic nucleus and are derived to as derivatives of benzoic acid. IUPAC system. The IUPAC names of carboxylic acid are obtained in accordance with the journal IUPAC rules, the suffix used for carboxyl group being oic acid. Carboxylic acids have a carboxylic group attached to an alicyclic ring and are named by adding the suffix carboxylic acid to the name of the ring. The carbon atom of the ring carrying the carboxylic group is always taken as number 1. The simplest aromatic carboxylic acid is named as benzoic acid. Other aromatic salts are named as derivatives of benzoic acid. Salt of carboxylic acid are named by writing the name of cation followed by the name of acid in which the ending is acid. Ic acid has been replaced by 8. For example, CH3C double bond O Na is sodium acetate. CH3CH2CH2CO NH4 is ammonium butyric. Some common names of compounds and their IUPAC name. Compounds common name, IUPAC name. HCOH formic acid, IUPAC name methanoic acid. CH3COH a common name acetic acid, IUPAC name ethanoic acid. CH3CH2COH propanoic acid, IUPAC name propanoic acid, and many more. Benzene ring C double bond OH benzoic acid, common name IUPAC name benzoic acid. Structure of carboxyl group, acidic character of carboxyl group. Even though the carboxyl group is generally represented by the structure C double bond OH, actually it is a resonance hybrid of the following contributing structures. However, there is a separation of charge in structure 2 and therefore it is less stable than structure 1. As a result, these two structures don't make equal contribution to the resonance hybrid contribution of structure 2 being much less important than that of constituently 1. The resonance energy is low. It is evident that in the present resonance hybrid, oxygen of the hydroxyl group carries some positive charge. As a result, the electron pair of the OH bond is largely displaced toward oxygen. Due to this displacement of electron pair, the hydrogen of the OH bond can be released as H positive ion with the simultaneous formation of carboxylate ion. This is responsible for acidic nature of carboxyl group. It can be easily seen that the two contributing structures of carboxylate ion, third and fourth, are equivalent to each and other, and therefore they make equal contribution to the resonance hybrid. The greater stabilization of carboxylate ion tends to push the equilibrium in the ionization process towards the right, and thus this constitutes the major factor in the dissociation of carboxylic acid. On the other hand, formic acid gives two values of carbon-oxygen bond lengths. This showed that in formic acid, CO bond has a greater double bond character while COH bond has a greater single bond character. Orbital structure. The resonance in carboxylate ion can also be understood in terms of molecular orbital concept. In terms of this concept, the carboxyl carbon atom is in a state of sp2 hybridization. These hybrid orbitals are directed towards the corner of triangle and lie in the same plane at an acid of angle of 120 degree with each other. These three orbitals form the 3 sigma bonds, one each with 2 oxygen atom and a 3 with alpha carbon atom. The remaining unhybridized p orbital of the carbon overlaps sideways with the p orbitals of both the oxygen atoms to form a delocalized pi molecular orbital. In other words, the pi electrons are not confined to the nuclei of the atom because they get disturbed around the nuclei of three atoms. This delocalization of pi electrons leads to the stabilization of an ease of formation of carboxylate ion. Comparison of acid character of alcohols and carboxylic acid. Both alcohol and carboxylic acid contain OH group in their molecule, but alcohols are practically neutral compounds while carboxylic acids have acidic character. This is due to the fact that carboxylic acid contains C double bond O group attached to the OH. This enables both carboxylic acid and carboxylate ion to exhibit resonance with the latter and being more stable than the former. As a result, carboxylic acid get dissociate to form H positive ions and carboxylate ion. On the other hand, neither alcohol nor alkoxide exhibit resonance, therefore they don't dissociate to an appreciable extent and are practically neutral in character. Comparison of acidic strength of phenols and carboxylic acid. Carboxylic acids are stronger acids than phenol. This can be explained in terms of stability of carboxylate and phenoxide ions. On comparing the structure of carboxylate ion and phenoxide ion, we find that the negative charge on the carboxylate ion is dispersed over two oxygen atoms, which in phenoxide ion is present in only on one oxygen atom. The charge dispersal on two oxygen atoms leads to greater stability. Hence, carboxylic acid is more acidic than phenoxide ion. General methods of preparation. The first method of preparation for carboxylic acid is oxidation of primary alcohols or aldehyde. Carboxylic acid can be readily obtained by the oxidation when we oxidize primary alcohols or aldehyde. The usual oxidizing agents employed are acidified potassium dichromate, potassium permanganate or nitric acid, which will be RCH2 or RCHO, and by oxidation they are converted into RC double bond OH, that is carboxylic acid. For example, isobutyl alcohol, which is CH3, CH, CH3, CH2OH, and in the presence of K2Cr2O7 and H2SO4, it will be converted into CH3CH, CH3C double bond OOH, which is isobutyric acid, and benzyl alcohol, which is benzene ring, CH2OH, in the presence of potassium dichromate and sulfuric acid, it get converted into benzoic acid, which is benzene ring, C double bond O and OH. Aldehydes can be oxidized to corresponding acid by mild oxidizing agents. The method is highly selective as it will not oxidize any other oxidizable group such as alcoholic group if present in the starting aldehyde. Oxidation of alkyl benzenes. On heating alkyl benzenes with oxidizing agents such as acidified potassium dichromate or acidified alkaline potassium permanganate, the alkyl side chain get oxidized to carbonyl group. The reagent commonly employed is alkaline potassium permanganate. This constituent a useful method for the preparation of aromatic acids, and the alkyl chain is always oxidized to carboxylic acid irrespective of the size. Third, hydrolysis of nitriles. Hydrolysis of nitriles with an aqueous acid or alkali is an important method for preparing carboxylic acid, which is RC triple bond N plus 2H2O in the presence of H positive or OH negative will give RC double bond OOH and NH3. And the same happens when propyl nitrile is reacted with H2O, HCl, it will give propanoic acid plus NH4Cl. Hydrolysis of acid derivatives such as acid chlorides, anhydrides, esters, amides. The acid derivatives mentioned above can be hydrolyzed to produce carboxylic acid with varying degree of difficulty, while acid chlorides and acid hydrides are hydrolyzed with water. Such as hydrolysis of esters or amide is carried out in the presence of mineral acids or alkalines. Acid chloride plus water will give carboxylic acid plus HCl. Mechanism. Fifth, carbonation of Grignard reagent. Carboxylic acid may be prepared by the reaction of Grignard reagent with carbon dioxide followed by decomposition of the addition product with dilute mineral acid. This reaction is often referred to as carbonation of Grignard reagent. The carbon dioxide may be employed either in gaseous form or preferably in solid form. The mechanism of addition of Grignard reagent is to carbon dioxide is too similar that as to the addition of to aldehydes or ketones. The nucleophilic organic group of Grignard reagent adds to the electrophilic carbon of carbon dioxide, while the MgX part goes to on the oxygens. Malonic ester and acetoacetic ester synthesis. Mono or dialkyl derivatives of acetic acid can be easily obtained by malonic ester and acetoacetic esters as described below. Seventh, hydrolysis of trihalogen derivatives. Trihalogen derivatives having all the three halogen atoms attached to the same carbon atom gives carboxylic acid on hydrolysis with alkali. RCCl, which is trihalogen derivative, plus 3 moles of water will helps in removing of H from water and Cl from the compound, which exhibit that HCl is removed and RCOH forms, which is unstable. Then loss of water will take place and then the final product carboxylic acid is formed. Oxidation of methyl ketones, haloform reaction. When treated with sodium hypohalite, methyl ketones are oxidized to sodium salts of carboxylic acid. Sodium salt of carboxylic acid. These salts are acidified to get the carboxylic acid. For example, 2-pentanone in the presence of dilute HCl will give butanoic acid. Arnold-Estert homologation. This is a convenient method of homologation of acid, that is the conversion of a given acid into a next higher, for example, static acid. It helps to increase the numbers. For example, it converts lower carboxylic acid into higher carboxylic acid with the help of SOCl2, CH2, NH2, Ag2O and water. From alkoxide, sodium alkoxide reacts with carbon monoxide under high pressure to form sodium salt of carboxylic acid. This yields to free acid on acidification with dilute mineral acid. From alkenes, the method consists in heating an alkene with carbon monoxide and steam under pressure 573 and 673 in the presence of phosphoric acid, ethane to propanoic acid. The reaction involves carbohydroxylation of alkenes and is known as Koch reaction. Physical properties. Physical state. The lower aliphatic acids such as formic acid, acetic acid or propanoic acid are colorless liquids having sharp irritating smell. The acids from C4, C9 are colorless oily liquids having somewhat unpleasant smell, but the higher members are colorless waxy solids having practically no smell. Aromatic acids too exist as colorless solubility. The aliphatic acid adds to CH4 in the solubility. Boiling point. Carboxylic acid from intermolecular hydrogen bonds and therefore they exist in the hexated molecule. Melting point. The melting point of acid containing even number of carbon atoms are higher than those of immediately lower as well as immediately higher homologous containing odd number of carboxylic acid. Chemical properties. Reaction due to ionizable, that is the cleavage of OH bond. Acidity. All the carboxylic acid ionize in aqueous solution and exist in equilibrium with the carboxylate anion and the hydronium salt. Thus, they exhibit considerable acidic character. Salt formation. Carboxylic acid are attacked by strongly electropositive metals such as potassium, sodium, zinc to form their salts and liberate hydrogen. They also react with bases such as hydroxide, metallic oxide, bicarbonates to form salt. It may be noted that, however, the carboxylic acid are much weaker than mineral acid like hydrochloric acid, sulfuric acid and nitric acid. Therefore, the salt of carboxylic acid are rarely decomposed by treatment with the mineral acid to regenerate carboxylic acid. Reactions involving representative for hydroxyl formation of functional diet. The OH part of the group can be replaced by Cl, OR, NH2, OOCr, that is to acid chlorides, esters, amide, anhydrides, etc. Third, formation of ester. When heated with alcohols in the presence of a strong mineral acid such as HCl, H2SO4 or Lewis acid, which is BF3, carboxylic acid form esters. This reaction is reversible in nature, known as esterification. For example, RC double bond OH, HOR dash alcohol, H positive, RCOOH dash ester plus water. This is generally achieved by using a specifically designed device known as Dean Stark separator, and it is generally When the reaction between the carboxylic acid, that is a C double bond OH, and alcohol, which is OH group, to form an ester is carried out in the presence of HCl, which is hydrochloric acid, which is present in gaseous state, is often called as Fischer-Spire esterification reaction. Formation of anhydrides. When treated with acid chlorides in the presence of pyridine, carboxylic acids form the corresponding anhydrides. Carboxylic acid, acid chloride, pyridine will give acid anhydride, pyridine hydrochloride. Reduction. Carboxylic acid are resistant to catalytic hydrogenation. However, they can be reduced by lithium aluminum hydride to primary alcohols to carbonyl part of carboxyl group getting reduced to CH2. Carboxylic acid in the presence of lithium aluminum hydride will be formed into primary alcohol. The reduction process via the formation of an alkoxide which yields the alcohol on the hydrolysis mechanism. The reaction involves the nucleophilic attack by hydride ion, that is H from lithium aluminum hydride on carbonyl carbon. The carboxylic acid is reduced initially to aldehyde and finally to the primary alcohol as shown ahead. The reduction of an acid can also be brought by first converting the acid into ester, which is conveniently reduced to alcohol. Ballment-Blanc reduction. Elimination of carboxyl group. It is possible to eliminate the carboxyl group from an acid to form different products, such as illustrated by the following example. 8th, which is decarboxylation. Simple carboxylic acid get decarboxylated to form hydrocarbons when their sodium salt are heated with soda lime. What is soda lime? Soda lime is a combination of sodium hydroxide, which is NaOH, plus calcium oxide, which is CaO, or quick lime we can say. Mechanism. The reaction takes place through the loss of a molecule of carbon dioxide from carboxylate anion to form a carbanion, and once formed, carbanion gets protonated to form hydrocarbon. RC double bond ONA plus NaOH in the presence of CO will give hydrocarbon plus Na2CO3. Effect of substituents on decarboxylation. Since formation of carbanion is the key step in the above reaction, any factor which increases the stability of carbanion should increase the ease of decarboxylation. Kolbe electrolytic reaction. Electrolytic decarboxylation. Alkali salts of carboxylic acid on hydrolysis get decarboxylated to form the distillation of calcium salt of acid. When distillated in the presence of air, calcium salts of acids give different products as both distillation of calcium formate distillation of calcium formate yields formaldehyde. Calcium formate is HC double bond O, Ca. And when we heat it gives us HCHO, which is formaldehyde, and CaCO3. Second, distillation of a mixture of calcium salt of formic acid and calcium salt of another carboxylic acid gives an aldehyde, RC double bond O Ca, which is calcium salt of carboxylic acid, plus HC double bond O Ca. In heat, it will give 2RCHO plus 2CaCO3. Distillation of calcium salt of an acid other than formic acids gives a ketone. Ninth, Kolbe electrolytic reaction. Electrolytic decarboxylation. Alkali salts of carboxylic acid on electrolysis get decarboxylated to form hydrocarbons. 10th, distillation of calcium salts of acids. When distillated in the presence of air, calcium salts of acid gives high different products as given below. Distillation of calcium formate yields formaldehyde, HCOCA formate into formaldehyde. Second, distillation of a mixture of calcium salt of formic acid and calcium acid to give distillation. Third is distillation of calcium salt of an acid other than formic acids gives a ketone. Decarboxylative halogenation, Hunts-Dicker reaction. The silver salt of carboxylic acid react with bromine or iodine in dry carbon tetrachloride to form an alkyl bromide or iodide with the loss of carbon. Kolbe electrolytic reaction, electrolytic decarboxylic alkali salt of carboxylic acid on electrolysis get decarboxylated to form hydrocarbons. The overall Kolbe reaction may be represented as 2RCONA plus 2H2O will give electrolysis to alkane, carbon dioxide, hydrogen and NaOH. Electrolysis of sodium formate however yields only hydrogen, not a hydrocarbon. 10th is distillation of calcium salt of acids when distillated in the absence of air. Calcium salts of acids yields different products as given. Both distillation of calcium formate yields formaldehyde. Distillation of a mixture of calcium salt of formic acid and calcium salt of other carboxylic acids gives phenaldehyde. Distillation of calcium salt of an acid other than formic acids gives ketone. 11th, decarboxylative halogenation, that is Hunts-Dicker reaction. Reaction of the alkyl or allyl group. 12th, halogenation of alkyl groups in the presence of small amounts of red phosphorus. The alpha hydrogen of alkyl group aliphatic carbon can be replaced by chlorine or bromine to form a halo acid. This is known as Hal-Bozard-Zielinski or simply HVZ reaction. For example, CH3CH2 C double bond OH, which is propanoic acid, in the presence of Br and P. It will give alpha bromopropanoic acid, which is CH3CH Br C double bond O and OH, and further it will react with Br2 and P and it will give away HBr and the formation of alpha dibromopropanoic acid, which is CH3CBr2COH, will take place. It may be noted that bromination takes place exclusively at the alpha position and the reaction stop after all the alpha hydrogen have been displaced, but chlorination can continue further in the chain after the displacement of alpha hydrogen. 13th, aromatic substitution. Aromatic carboxylic acid can undergo the usual electrophilic substitution reaction of benzene ring, such as halogenation, nitration of sulfonation. It may be recalled here that the carbonyl group is a meta-directing and deactivating group, and therefore the above reaction takes place only under vigorous conditions. Special reactions of formic acid. In the molecule of formic acid, the carbonyl group is attached to a free hydrogen atom. Therefore, formic acid combines the property of an acid and aldehyde required, which is carboxylic acid HC double bond OH and HC double bond O. Therefore, it undergoes certain reactions not given by other carboxylic acid. The important reactions of these types are oxidation. Unlike others, but like aldehydes, formaldehyde is readily oxidized to carbon dioxide and water. Therefore, it reduces to Tollens reagent to form a silver mirror and Fehling solution to a red precipitate of C2U. Formic acid can also be reduced and acidified. Potassium permanganate, acidified potassium dichromate and mercury chloride. Reaction with concentrated H2SO4. When heated with concentrated H2SO4, formic acid gives CO and H2O. Third, action of heat on sodium formate. On heating to 663 to 673 Kelvin, sodium formate gives sodium oxalate and hydrogen. Acidity constant of carboxylic acid. pKa value. These days, the acidic strength of an acid is also represented in the terms of pKa value, which is negative logarithm of the acidity constant, which is pK is equals to minus log Ka. For example, pK of acetic acid is 1, Ka is 1.75, 10 raised to the power minus 5 is equal to 4.75. It may be noted that the stronger acid has a larger Ka value but a smaller pK value, while a weaker acid have a smaller Ka value but a larger pK value. Most of the simple unsubstituted carboxylic acid are moderate strength, having a pK value of 3 to 5. Effect of substituent on acidity of carbon. An electron withdrawing group, say G, on the carboxylate anion attracts electron towards itself and thus disperses the negative charge of the anion, and as a result it stabilizes the carboxylate anion and thus increases the acidity of the parent atom. An electron releasing substituent on the carboxylate anion intensifies the negative charge of anion, therefore destabilizes the anion. Aliphatic acid. Important conclusion. It is quite obvious from the discussion, the stronger electron withdrawing group present in an acid, the greater is acidity. For example, fluoroacetic acid is stronger than chloroacetic acid because fluorine is a stronger electron withdrawing than chlorine. The larger the number of electron withdrawing groups present in the acid, the greater is the effect on the acidity. That is why we find that dichloroacetic acid is stronger than dichloroacetic acid, which is stronger than monochloroacid. Third, a group having electron withdrawing inductive moves away from the carboxylic acid. Its effect on the acidity becomes less pronounced. This is quite in keeping with the fact that inductive effect falls off rapidly with the distance. This is why alpha chlorobutyric acid is weaker than beta chlorobutyric acid, which in turn is weaker than alpha chlorobutyric acid. Fourth, the effect of electron releasing group. The effect of electron releasing group is shown in table. It is apparent that acetic acid is weaker than formic acid because it contains electron releasing CH3 group attached to the carboxylic acid, while formic acid only has a hydrogen atom attached to the carboxylic group. Aliphatic acids and their pK value: CH3 C double bond OH 4.75, NCC CH2COH 2.42, etc. etc. Aromatic acids, benzoic acid. In discussing the acidity of aromatic, let us begin with the benzoic acid, which is simplest acid containing a carboxyl group attached to an substituted benzene ring. Phenyl group directly attached to the carboxyl group exerts an electron withdrawing inductive effect, but at the same time it tends to release electron towards the carboxyl group due to the resonance effect. Now the plus R effect in this case is more dominating than minus I, so that the phenyl group has a net electron releasing group. That is why benzoic acid is a weaker acid than formic acid. It may be noted that, however, that the new net electron releasing effect of phenyl group with benzoic acid less than the electron releasing inductive effect of alkyl group present in the aliphatic acid. Therefore, benzoic acid is a stronger acid than aliphatic acid. Form acetic acid, phenyl acetic acid. Let us consider the simplest aromatic acid containing the carboxyl group changed as phenyl acetate, stronger acid. Effect of substituents on the acidic strength of aromatic acid groups: having electron withdrawing inductive effect as well as electron withdrawing resonating effects such as NO2. Let us consider the effect of the presence of nitro group on the benzene ring on the acidities of aromatic acid. Nitro group exerts an electron withdrawing inductive effect as well as an electron withdrawing resonance effect. However, it may be recalled that resonance effect operates only in ortho and para position, therefore being hardly ineffective on meta position. This means that by resonance mechanism, the nitro group cannot be marked reducedly the electron density. B. Effect of halogens. Halogens have electron withdrawing inductive effect and electron releasing resonance effect, but the inductive effect is stronger than the resonant. To understand the effect of presence of halogens on the acidity of aromatic acid, let us make up the case of meta and chlorobenzoic acid. When chlorine is present at para position, para is the totally opposite position. Its electron withdrawing inductive effect is opposed by its electrons releasing resonance effect. However, since the inductive effect is stronger than the resonance effect, overall effect is electron withdrawing with this, so that carboxylate ion get destabilized. As a result, P chlorobenzoic acid is stronger than normal benzoic acid. So that is the reason why we say that chlorobenzoic acid is a stronger acid than benzoic acid. The effect is para position and electron releasing resonating effect. When chlorine is present in meta position, only its electron withdrawing, that is inductive effect, operates. Since there is hardly any resonance effect operating at mesa position, as such there is a strong electron withdrawing effect, so that the carboxylate anion is much more stabilized. That case of isomer. Hence M chlorobenzoic acid is even stronger than P chlorobenzoic acid. Benzoic acid is found to be stronger than both meta and para isomers due to ortho effect. Thus, the odorous acidities is benzene ring and when Cl is ortho position is more acidic than meta and then meta para and normal benzoic acid. Groups having electron withdrawing inductive effect and electron releasing resonance effect, but resonance effect is stronger than inductive effect such as OCH3, CHOH. Let us consider the effect of hydroxy group when present in meta or para position. Example of hydroxybenzoic acid. Hydroxyl group has only electron withdrawing inductive effect but an electron releasing resonant effect, and the overall effect may be explained as follows: due to its electron withdrawing nature, of inductive effect, it tends to decrease the electron density at all position, but at the same time it tends to increase the electron density at para position due to resonance mechanism, while the meta position is not markedly affected since the resonance effect is more powerful than the inductive effect. The net result is that there is an increase in electron density at para position. On the other hand, only electron withdrawing inductive effect operates at meta position, so that there is a decrease in the electron density at the meta position. Thus, the hydroxyl group present in the p-hydroxybenzoic acid exerts an overall electronic releasing effect and destabilizing effect on the carboxylate anion. D. Groups having only one electron releasing inductive effects such as CH3 or CH2, CH3 groups. Such groups have an acid weakening effect when present in para and meta position, but the effect is relatively more in meta position. Therefore, the order of acidic strength is that present in the meta and para. Normal is more acidic. Exceptional behavior, ortho effect. An unusual observation is that practically all groups when attached ortho to a carboxyl group in aromatic acids increase the acidity. This anomalous behavior of groups when present in ortho position is known as ortho effect. However, it has not yet been possible to explain this behavior completely. The acidities of some simple and substituted aromatic compounds are given below. Test of carboxylic acid. Carboxylic acid can be detected by following test, which are as follows. Carboxylic acid turn blue litmus red first, and the second is they give effervescence with the liberation of carbon dioxide when added to a solution of sodium bicarbonate. When a carboxylic acid is heated with alcohol in the presence of a small quantity of concentrated sulfuric acid. Sulfuric acid is H2SO4. A pleasant smell is produced due to the formation of an ester. So that is all about the behaviors. The first one is effect of substituent on acidic strength. We have discussed that when electron withdrawing inductive effect as well as electron withdrawing resonance effect is there. And the second one is the effect of halogens. Halogens have electron withdrawing inductive effect and electron releasing resonance effect. And the third one is groups having electron withdrawing inductive effect and electron releasing resonance effect, but resonance effect is stronger than inductive effect we have discussed, such as OCH3 and OH groups. And the fourth one is groups having only electron releasing inductive effect such as CH3 and CH2, CH3 groups. And the last one, that is exceptional behavior, which is at ortho position, and the exceptional behavior is observed in ortho position, increases the acidity. So, and we have discussed the test. So that all about the chapter carboxylic acid. Thank you.